So I am recording towards the end of the day here. Um, After I've kind of languished around trying to talk about this design I have in regards to my 49cc opposed piston. So I watched Driving for Answers video on this single stroke in engine analyzation that he did. And I was like, oh, that's really cool. And he points out a lot of the flaws that I actually have, except I haven't finished it completely, for the fact that the wavy part, disc that he was describing, that has to not be at the top dead center. It's like it always has to be already opening. And so like that degree of resistance during its opening, basically it can fail. It could go backwards, and so they always have to have it already having it go down, just like any other crankshaft, right? Now, the reason why I'm talking about it is because that also means that it's always accelerating away during its actual combustion cycle, which is really, really frustrating. A degree of resistance there allows for a continuation of complete burn without an expanding cylinder, which means a more efficient burn, which means more power. And he correctly points out that it doesn't really have a lot of torque. And I wanted to talk about how my hydraulic fluid piston crankshaft design happens to have actually a very good amount of torque. But the reason why is probably different than you might expect. So he described a crankshaft as like, this lever. And he's like, that's perfect. That's it. That's literally what that is. But the way I describe my hydraulic fluid, torque or horsepower pressure converter to torque is a turbine like anything else. All right. So that's all they are. They're converters of pressurized fluid to torque. So that's all they do. All right. Now, the reason why I wanted to talk about that is because as it goes from this side and it spins, ultimately this, but then it doesn't just spin that, it goes over to this side, both sides, and that also spins. But this one's connected via another line, and so that acts like its own version of a flywheel as the fluid moves. Now, it's from center out, side, back to center. Now, the reason why I talk about this is because it imparts a greater degree of moment of action into that fluid, capturing more of its given pressure into gaining torque. But hold on, because you have to describe it like a plate that has many, 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 many levers. But then you have multiple plates that have many levers as a result of that. All right, so that's what that is. But then you have the top bottom, which is the return line. And then you have the two sides, and then the two sides on the opposed piston. Now there's a seal. I've already described how that seal works. You can go through any of my other videos. But the basic principle is it's multiple sections with some piston ring-like seals. All right, so that way a asterisk style connecting rod, all right, but it's forged, it's all one piece, is able to slide through that, and it has to be slightly tapered. So that way, during its most increased compressed moment, it's able to be very, very sealed, and it can't go as easily further beyond where you want it to go to. All right. Now, it still works. It can handle the pressures, and we have a little, oil line for it that runs the length of the tube. By we, I mean I and this imaginary, group of people that wanted to invest in me, and eventually created a business. That's kind of the point. Like these are my aspirations. These are my goals. Anyways, moving on. It goes through a sliding valve that's there that as it rotates during its middle dead center, outwards, it fires a little bit of oil to its oil ring and allows for that to still have proper lubrication. Now, it doesn't just fire it in, it also sucks it in towards the other side using the scavenging method. But it's a little bit further down as it pressurizes it, all right? And then a little bit further down as it travels, because it's oval, it allows for that return of that oil to go back in. All right, so like that's what that is. I have a valve there, effectively. It's a really easy way to get around the sealing issue and still having the lubrication issue solved. It's still going to burn some oil, but all engines burn some oil, so I don't really ever give a fuck for what it's worth. So that's what that is. But then there's sliding valve ring designs. Now, the reason why I wanted to talk about this is because not all of that, it's just about, because I've already gone through that quite a bit. I wanted to talk about the fact that it's like, this is more torque over time, no matter what. Like, it's more torque than 8499cc. In fact, it's more torque for this design, period. Like, just straight period. Like, it's, but see, the problem is it's not a toroidal, and not a typical turbine blade system. It's a tube system with multiple little holes throughout blades, with an end to out to end, kind of like a diamond shape, sort of design to capture as much as it goes through. But then I need it to turn much harder. So instead of like in and then out and then in and zigzag, none of that's going on. It flows through, but I'm using stators that are inside of the blades and holes inside of the blades that effectively make it turn and impart a much greater degree of cavitation during those moments around the blades / structures, I suppose, that is. Because it's like, how is it a toroidal? And it's like, well, I mean, technically there's some degree of toroidal, especially since there's a ring around that's there constantly. So that way it can impart that, let's see here, because we have a gear on the outside, or more like another version of this that goes from the outside of the cylinders as it rotates that to the side turbines, and then that imparts that degree of spin too, while the inside also pumps it to this side, and then it has to go back up and down with alternator style turbines. Now, see, these are just to help with the flow to go faster. We don't use any hydraulic or electric motor designs. They are alternators specifically because we want to monitor the flow rate to make sure it returns appropriately with the little cavitation tubes that have little boundary layer cavitations, so that way it flows faster into the given cavity at the top and bottom. So like that's another version of just piston seals. And then it goes into top and bottom. And so as it flows, it goes down, and then we have the inside of the opposed piston and then the outsides of the opposed piston as being combustion zones. That's the case. I want to move on from that because it's like you would have to actually listen to a lot of that already, or have already listened to it. But the basic principle in design is that there's a exhaust tube within inside of that tube that connects the inside and outside, and it recycles some of that exhaust, but also, as it does even truly affect, kind of like a carburetor, with a pressurized exhaust or intake manifold that then sucks a degree with the valve that's there with a spring that's like a blow-off valve. So one side gets lower, that side has enough pressure, it blows it in because the nozzle is of the right diameter to allow for a higher degree of pressure, and so it flows together with that. And that's an acoustic pump. That acoustic pump, during that increased degree of fluid flow and decreased pressure, but then like this little area of valve is like a ring valve. So it's like it blows air in around that tube area, creating a faster degree of flow around that afterwards. So it's kind of like a funnel sort of design. Anyways, this creates its own version of an acoustic pump that also creates vortexing. During that exhaust, some of that exhaust that we want to actually exhaust is light, much, much lighter. Okay, so that exhaust is mostly H2O and O2. Brake mean effective pressure now goes way higher, as we do have air coming in, and then I use a transformer-like design for my spark. my spark is not a standard spark plug with a electrode and gap and the ground. It is instead the cylinders are grounds along with like other places alongside the cylinder and the head, because of course there's contacts there. All right. Now, also, we're sucking out electricity utilizing the correct electrical setup here. It's a good way to put it is like a neon transformer. So I call it a transformer. But then it's also, we have the right, we're putting a bunch of voltage into it. So we're sucking out and we're putting voltage in, and we're going to basically, as we fire and spurt in a bunch of fuel. I mean, it already has air in there. So now we're a version of a compression ignition, spark ignition hybrid design, as it's very hot, very compressed, but then we're also firing in fuel that's actually so close together and very high pressure that that's where our high voltage goes through, as well as it tries to head towards the leads. What this does is it increases a degree of the exothermic reaction for lower amounts of fuel, but also it happens to separate a large amount of the carbon off of oxygen as it exothermically recombines again. Then, as it spins in vortexes and creates that acoustic pump, we happen to have areas of high pressure that happens to have very high densities of these carbon graphite nanoparticles. That then gets fed into a graphite catch can. All right. Now, if you don't know anything about anything that I just said, you need to brush up on some physics and engineering. Okay. These are all real things. These are genuinely things that do happen and are things that are real. Okay. They already are things we use today. These are genuinely those things. I'm not blowing smoke up your butt. They are already things that occur, okay? We already use them. We already know that this is a thing that works this way. Now, the reason why it works this way is we still have a bleeder, we still have the exhaust come out, and we still ultimately have intake coming in. Fuel pressure is still very high because we also happen to have, during that spin, a degree of this rotating back and forth pressurized fluid area that squirts in fuel during a moment when it is at the correct timing, as we change that timing with the solenoid. All right, now that opens up and it's firing in with the electrode, which is the fuel now, which has carbon and all the rest of it, which will, no matter how much voltage you put through it, still ultimately fire forward and lance an arc, especially when you happen to have the transformer trying to suck out electrons. So it travels quite far, exothermically reacts, and it'll initially deflagrate, compress towards the center, detonate, and then that will then rebound off, and then ultimately bounce and fire more fuel as we can continue to fire fuel in, but we can cut the electricity, but actually we don't. And by we, I mean I. My design does not stop electricity. It continues to pump electricity in. The reason for this is very simple. It exothermically reacts, not exothermically, it electrostatically, which is kind of an exothermic kind of reaction. Point is, removes a lot of the bounds, the bonds here that are attached for our oxygens and carbons and so on. And as it goes through a depressurization and then repressurization, as it'll send it back towards the center, it allows for that heat to be transferred towards the center, but also allows for that center heat to be transferred outwards, keeping a nominal amount of pressure, but then we remove a certain amount of pressure and then we gain the right amount of air-fuel ratio as we can burn appropriately for that area. We being me, or anyone else that wants to experiment and try this, just make sure you know that it's John Tyler Lemke's design. That's me. So there's that. But that's what that design does, and it's a single stroke, dual compression ignition, spark ignition, like a direct injection, not ignition design. The reason why I wanted to talk about this is because that engine that they have for that one single stroke does not have torque. It does not have torque. I hate that torque. Mine has torque. The reason why I'm continually saying that is because I have what is essentially a bunch of turbines, but they're separated and they allow for proper flow. And I allow for the correct flow to the top and bottom, and I still get compression, and I still have it because compression is also helped by the outsides and insides depending on the given, power. And now if I scavenge it, meaning power stroke, I'm able to do that continuously. Just so you know, I'm able to do that continuously, and I need less and less and less flywheel for more and more of that compression because the compression is handled by the combustion of another event on the outside or inside. As a result, I get more and more torque. So I create a pressurized heat vessel that is like a Stirling engine, which happens to have enough lower pressure on another side compared to where it's combusting, that I'm able to maintain very high efficiencies, very high brake mean effective pressures, and extraordinarily high amounts of torque because of the turbines from the sides and the other sides. And then these are just alternators. The reason why I have them as alternators is I can dynamically change the load on those alternators and allow for the proper flow rate to both sides with the correct valving to ultimately make sure I never have any change of where my center is. I basically always keep the same center, so I always keep the same compression ratio, so I always ultimately have the same resonances and therefore end up getting very, very good peak efficiency. As a result of this, I then am able to capture a lot of the carbon. I still have some exhaust come out. It's still going to go through another resonator. So this is a whole brand new design right now. So it's 3-to-1, all right? But then that goes into a high flow kind of like style resonator where it's a bunch of holes or slots in a given larger chamber, then it comes out at the same size of hole diameter on the outside. Well, this same kind of design, but I had put piezoelectrics and a different geometric style design to allow for a very specific set of vortexing and resonating pressure waves. That way I still have the scavenging effect and it still produces a capture of that pressure inside of that volume, and I don't have as much go back in while I have a lot more go out. Then I have my turbine, which is a similar design, which is, okay, so those piezoelectrics create electricity. So just so you know, we're creating piezoelectricity. But then also with that exhaust for the graphite catch can, another version of electron flow, because you have to create an electron flow to do this. And because I'm deciding to make that a version of static, we have to make that statically separated, not just with the acoustic pump design here that we have. I have to also use a static area. So that way it creates a vortex. During that static, it grabs a lot more graphite than it would ever anything else. As that graphite, with a little of the air that's still there, all right, will still come in to this catch can, which will have its own version of it's got cooling fins, but then also piezoelectrics, then also the right shape for a resonator that then allows for filtration as it creates centrifugal vortex, but also acoustic pump resonations to effectively precipitate and crash out. Bunch of words for graphite nanoparticles stay down and they don't go out. Because static and clean and resonant in pressure and separation, filtration effectively, and then exhaust goes back into turbine. Which turbine is another version of in to out, but this time it's zigzag with these other spins that have to happen during that. We want to create a vortex or vacuum, not vortex, on the back of the blades. But then there must be stators that are there, and there's a little scoop. And so those designs effectively mean that I grab a lot of that graphite. If there's any left, I'll grab all that graphite and a degree of that pressure, which then gets recirculated back. And goes through the catch can and gets recirculated back. So that allows for a very high efficiency turbine setup that then has a T design for the axle that's here. That then goes off into a housing for a super turbo effectively. So it's this is a clutch which has multiple step gears, which then changes, kind of like a Venerator, and then eventually disengages. And then that goes off into the turbo from the turbine, once it's at the right RPM, doing all the work, which is basically what a super turbo is. So then I was like, right, so condensing air during a funnel, ram air, while having like a degree of like these bullet shapes. Okay, so they're not teardrops, they're bullet shapes. So like a pointy nose, and then they're flat. But then there's flat with these little flanges, the feathers, effectively. So they helps separate the air, and then we have another degree of another bullet, and then we have little teardrops there. All of this is hollow that allows for water to go through for a water to air exchanger. That goes through another version of a in to out to in approach for allowing for compression by using a spinning blade, fan blade, but it spins from the hub, and it still has an axle, but it's what it is. And then that goes through another version of a water to air, which is a bunch of like effectively stators, solid flat pieces that go from larger to smaller with the funnel and compress it and then realign it. Then it goes to an air to air, which is a condenser, which has a bunch of other stuff. It doesn't really matter. Point is, larger diameter to smaller as it cools, so that way it increases flow, but then it's not just increasing flow, it helps with condensing. As it cools, it gets denser, blah, 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 blah. Lots of words and lots of fancy speak for it's now the coldest, densest air that we can get that's very pressurized and high flow rate. Okay, now that's for that to go into this, which is the ring sliding gears, which can go out and in to open up and change its size of the valve, because there's multiple little valves around the ring that then also, as they rotate, change their duration as they can come in faster. But then, because that's the hydraulic fluid with a gear, okay, which gives me timing, duration, and ultimately same thing for the exhaust. All right, which gives me my scavenging, which gives me all the things for both the inside and outside, and it's still very much with those little, roller bearings that keep it very stable and pressured against this. Still has a fluid on both sides. It sits in with bearings and they're moving track inside of the tube. Effectively, it's just like, oh, it's sealed. Shut up. It's very sealed. Shut up. I don't care what you think. It is. Literally be quiet. That kind of thing. Like, I hate it when people like try and talk to me about that, because it's like, no, it's sealed. It's very sealed. It's basically perfectly sealed. Like, very, very perfectly sealed. But it's always rotating with the whole thing. So instead of like, oh, it's only a little bit, and it goes back and we need springs or anything. No, it's always spinning, because there's multiple little, moments where it can open, but like there's moving on. Doesn't really matter. Point is, that's also one of the reasons why those tops and bottoms pieces for that are there too, because that also helps the rotation of this occur. Same thing for the outside. All right, so that's a lot of crankshaft, basically, this fluid, but crankshafts have this issue of this weight has to balance it and it has to go up, and you have to lose a degree of your pressure, which you're already losing as it expands, into that motion of lifting that weight to balance it. Well, now I don't have to do that. I literally don't care about that. I just have to flow it back in. And so like a lot of that's a large amount of torque that happens to be imparted while also allowing for the correct degree of fluid flow, because we have little boundary layer effects on the insides of these tubes that allow for it to skip off of those cavitation areas instead of stalling. Then it allows for higher flow rates. And that also happens to protect those areas from water pressure, or in this case, hydraulic fluid pressure, literally disintegrating the inside of the engine. We happen to have ceramic and aluminum composites, meaning ceramic over top of aluminum. By we, I mean me. This is my design. And that allows for it to effectively use those stalling and then cavitation areas to properly fluidically flow with less resistance from boundary layer, and therefore greater degrees of captured torque energy with these designs. All of that is to say, that's why this is the single stroke model, and it has an ECU that basically changes it from 4-stroke to 2-stroke with the scavenging, and then straight up to 1-stroke, which it moves exhaust from side to side, and we just blast in fuel by pushing in high pressure air, and then we then allow for it to go through with the electrolysis process or electrostatic, whatever it is that they'll call it. To me, it's like it's a Lemke cycle. It's a real 1-stroke that's using a bunch of heat and pressure and acoustic pump resonance and blah 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 blah, all a bunch of lingo. That means with the electricity that's there, I'm breaking apart the carbon oxygen bonds, and then I'm allowing them to combine back into carbon graphite, and then taking and extracting that carbon graphite, but then allowing for exothermic reactivity for hydrogen and oxygen to continue to build up, and then eventually it goes out, and we always bleed that out. And so like a degree of that fuel is used to help separate and become ultimately more efficient, more powerful, but more clean. I have a much higher brake mean effective pressure, and that means I have a much greater degree of foot-pounds of torque. Captured foot-pounds of torque too, which then turns into why I say it can go up to 50,000 RPM, and why I also say I can have 500 foot-pounds of torque, but then that's capped. I cap that torque. Like that's valves and little solenoids and everything to essentially mean for my ECU that you don't have danger occur riding a 49C, which by the way, this thing is not super, super big. It's the size of like one of those handheld coolers. You see them in TV all the time for like, oh, we have to get the heart somewhere, to transplant the heart's got to need to be, that kind of thing. Kind of same size. Think about it like slightly longer, in terms of like its width, but then it's the same degree of that and then same degree of height. So kind of that kind of style, but it's a whole engine block instead of like 49cc. And my whole idea was, well, if I have 500 foot-pounds of torque to give you and up to 50K, which I can do that, and I can maintain that because like that's the reason why brake mean effective pressure and exhaust recycling and all this stuff makes that occur. It's also one of the reasons why it's super dangerous. It's also $1,000, and I'm using basic bitch material, aluminums, ceramics, and chromoly steel with ceramic on the inside, and then same thing with the pistons and the correct seals that are not actually as expensive as you would think because they're metal ceramics or rubber plastics that happen to have a degree of ceramic to handle higher heats and pressures. All right, so they're not really metamaterial. These are already out on the market now, but the reason why I talk about it is because it's like, well, there's already engine coolant around the hydraulic fluid, which is also just hydraulic fluid, but I have this nice little design. This has been changed for my original design for a waste heat generator. So it's a radiator that happens to have piezoelectrics in a hollow fin array that allows for another degree of very, very low pressure insulative oil. So it's a hydraulic fluid that's meant to transfer. So like that's just an exchange of, some fins on one side and another. And like that's its own piezoelectric area because like I can just stick that and then bolt it and then seal it because that's easy. But then it's like that's off to be pumped into utilizing some of the crankshaft and some of the electricity here that's being made into this resonator Joule-Thomson cycle race heat generator radiator. So it goes through a small to a large to a large, and it has to go through that in a given way with fins that are there. All right. Now, as a result of this, as it expands, it loses heat, and it uses that expansion of that lost heat to then help cool the next one. Okay, that kind of thing. Joule-Thomson cycle, right? But then we're using that heat transfer off into this cooler area, which is the fins, which is the little lower pressure fluid that's oil, that's insulative. So we have to have piezoelectrics here, and then they are very specific fin shape and size. So they're not super specific. They can be broken or whatever, chipped and so on. They're not going to stop, making it so that way it works. But they're all connected in a series of arrays with, the standard field effect. And in this case, we want to use field effect MOSFETs because that allows for all of that heat, which there's a lot of, as it expands and contracts and resonates with that expansion and contraction, utilizing like that acoustic pump design effectively as it expands it, because that creates pressure wave oscillations, which we capture in the stators and the fins. But also that heating and cooling also produces its own degree of piezoelectric energy, because that's mechanical strain to electricity. If you don't know, now you know. These are crystals that take a pressure and then they produce electricity for us. You don't have to really cool them, if we're being honest, because you have to make sure the strain gets reduced, which is why vibrational efficiency here is key. So that's why it's like they're built with a Joule-Thomson and acoustic pump style to drain off a lot of that heat into a fin while also cooling themselves during that moment to then allow for a much greater increased efficiency of cooling, but also taking that energy from cooling, that work energy, and then imparting that work energy into becoming electricity for us. Okay, they're not work energy, it's electricity, but it's still energy that we can turn into work energy. That's the point I'm trying to make. So we have a lot of electricity from the waste heat from both the engine, transfer area, which is still, even if it breaks, even if the seal breaks, there's still hydraulic fluid. It will work. It won't kill the engine. This is a high performance hydraulic fluid, and this is a less high performance hydraulic fluid that's more meant for this to expand during this. That's the reason why we do that, because I don't want this in a low pressure. I want this higher pressures. I want it to be a little bit lower pressure to allow for that expansion during the heat transfer. Now, that's pump energy effectively, but then that's also capturing a lot more heat, because a lot more heat energy is there than the pump energy takes for that required energy to get there. Now, that means I have a lot of electricity to dump into this transformer spark setup for the 49cc opposed piston single cylinder. Again, 49cc. Even if I have 3 combustion zones, it's measured with bore and stroke. I have a longer stroke than I have bore, but I gain back for that degree of not so much big bore a huge torque because of the fluidic flow. That fluidic flow is what creates those larger and larger moments of action for levers, like mini, like you talked about for like a 600 something cc, but it has to be very, very high RPM. Well, now it's like, I don't really need that, because I make it much more efficient because I give it more and more time, and ultimately more of those levers over that time to gain back that pressure into torque. All right, so like that's the point I try and make. It's like, that's a cool engine. I don't like it because it doesn't have the torque, and it doesn't have the reliability in terms of like being able to make sure if anything fired incorrectly, it would go backwards, and that would be destructive to its firing and ultimately the engine's lifespan. So it's like it has to be very specifically done. And that's great. Mine is also. But if I wanted to have that fear, which I'm going to have, especially since it's using scavenging effects, and I use valves. Instead of the piston having that, I'm using rotating valves, which is why I can dynamically time, which is something that can never do. And I can change compression ratios dynamically as well, depending on how I want to do that with my spark and ignition. And I have 4, 2, and real 1 stroke to give you on both sides. So I can have it scavenge for a while, that heat, and then turn that into an air spring and give us more torque during the 4-stroke, especially with the exhaust recycler. This is the point I'm trying to make when it comes down to, hey, so if you aren't very well versed in engines, then you might not understand why this works. Or thermoacoustic pumps, or Joule-Thomson cycle, cooling, or piezoelectric electricity generation, or alternator generate, or turbines specifically, or hydraulic fluid, high flow rate application turbines. Like all of this is extremely high level stuff. And so, like, explaining this to someone that literally would know nothing about what it is I'm saying is difficult. And why these physics work the way they do, which is actually how physics work. Okay, like, talk to like an actual physicist. I'm not one, but you should. I've just learned enough to know about this. And so, like, that's the reason why all of these processes that I'm describing, well, it seems like I'm really animated, blah, 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 is because I'm very excited about the idea and the prospect of actually doing this. I know it will work. It's just getting the money and people really, and the machining and everything to do it. Like, that's all I need. It's like all of it works. It will work. There's nothing problematic about anything that I'm saying because physics literally has already been done on all of this. All of these physics phenomena already done. These are not reinventing the wheel concepts. So as a result, it's like, that's why I like my design more than theirs. It's just doing it better. That's literally what it's about. It's like, I'm doing it better, more efficiently, with ridiculous torque values. But that's also why that's a really high brake mean effective pressure, that it also starts off at around 3,000 something RPM, is around that 500 foot-pounds. And then 500 RPM is around the 313, 312 foot-pounds of torque is what it should have. But that's also where it ramps up. It starts the friggin' one-stroke process. It recycles and recircles the exhaust, and then ultimately builds up a massive amount of pressure, and then it drops back down into the 500 RPM range. So it's like there's a startup process to this, and then eventually you can just all the way up to 50K, because that's how the brake mean effective pressure problem works. Now, it's also the material designs here that are structurally built to handle this. Like, there's an outside engine block with a tube that's inside of that has this, and then another tube inside of that which has the coolant area, and then the oil area, and then all the rest of that, and then we have the gears, and then we have the actual cylinder, which is like chromoly steel, but thin because it has to have like this tube slide into it, but then it's thicker in other areas, and then it's supported in other areas. So it's like one of those things where you have to bolt, but then also like you're really just clamping this whole thing together, so that way those plates and everything spin very well, oscillates very well. There's some balance issues for what it's worth, because I don't have another one. Two of them literally changed some of those balances, but it's a single stroke 49cc. That's also why I would sell it to you as a $1,000 engine. But see, here's the thing. I'd also sell it to you with that exhaust manifold that is treated with ceramic and is vacuum insulated, with the resonator, with the graphite catch can, with the turbine that I talk about. Then it goes off into the actual muffler, because this is all designed for an actual motorcycle, but you can do it for anything, technically speaking. Same thing with the Ram Air, and then the all that other stuff. And then same thing with this cool manifold thing that I have that really increases, which I can talk about briefly, but it's effectively like, think thermoacoustic pump, but then like trapping the vast majority for the pressure right where the intake is. Instead of using resonances in an incorrect manner, I use pulses in a vertical, horizontal, and diagonal manner, with vortexing, to resonate a huge amount of this pressure in these areas throughout the RPM range consistently. It just actually adds more and more pressure the faster RPM goes, but then like that's actually kind of a good thing to a degree, because typically that higher RPM is only really something you're ever going to really do for the single stroke or scavenged two stroke design. the 4-stroke, it's like, well, I should give you a heads up that's 136, out up to that, depending on horsepower here, RPM that you're at. So it's like, 15K, we're at 15K. It's like, are you really going to run at 15K? I really doubt you're going to run at 15K. So, it's also one of those like, well, there's torque and RPM, but then there's altitude, and then there's a given amount of, fuel that you're using and all this other stuff. And so it's like, well, I give you the basic 136 horsepower off of the 49cc, and it's only going to weigh about 30 pounds for what it's worth, so it's very lightweight materials, blah, 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 blah. It doesn't really matter. Point is, it's designed specifically for that, but then it's like, right, but then you have to pay me $1,000 for the waste heat generator, radiator, the intake manifold as well, and all that stuff. Then you still have your spark and all that, and then the ECU, and so it comes with a whole package for $1,000, because it's only a 49cc engine. Yeah, it's a 49cc engine that does 500 foot-pounds of torque up to 50K, and it's like, yeah, but like at the same time, it's only a 49cc engine, and then it's like, I could put this in any fucking car and it would wipe the floor with anyone. How is it that you're fucking so angry about a 49cc engine costing $1,000 that gives you ridiculous high performance? So I don't know. I was kind of annoyed, but it was like $1,000 because of the way I can manufacture and design it. Makes sense for me with all of the things that I talk about, not just the engine, because like that's how easy that would be with the manufacturing designs and so on that I have. But it's like you have to, build up to that. So like that's what that is.